Have you ever just stopped and watched a rocket launch and really wondered how that massive, massive machine actually gets off the ground and into space? Well, today we're going to break down the fundamental science of rocketry. We're going to find out exactly how these incredible vehicles defy gravity and carry us to the stars.
All right, so let's just jump right in with a question that really gets to the heart of it all. If we want to go super high and super fast, why can't we just build a ridiculously powerful airplane? What is it about space that's so different that it demands a whole other kind of machine?
To get to the bottom of that, we're going to compare rockets to something we all know pretty well, the airplane. And by looking at what makes them similar, and more importantly, what makes them fundamentally different, you'll see why rockets are so special.
Okay, just look at the sheer scale of this challenge. An airplane, it cruises at what, about 10 kilometers up? A satellite in low Earth orbit, it's 50 times higher. And the speed difference? I mean, it's even more staggering. We're talking 550 miles per hour for a plane versus 17,000 for a satellite. That is about 100 times faster than a Formula One race car. So a rocket has to go way farther, and it has to hit these just mind-boggling speeds to even stay up there.
And here is the absolute key difference. An airplane's jet engine is what we call air breathing. It has to suck in oxygen from the atmosphere to burn its fuel. But what's in space? Right, nothing. There's no air. A rocket gets around this problem because it carries its own oxygen supply. It's a chemical called an oxidizer, and that right there is its superpower. Because it brings its own oxygen, it doesn't need to breathe. It's the only type of engine that can possibly work in a vacuum. So now that we know their secret weapon, let's kind of peel back the skin and take a look at the basic building blocks that make up every single rocket. From the little fireworks you see on the 4th of July to the absolute giants that launch astronauts into orbit. You know, every spacebound rocket is really made of 4 major systems, all working together in perfect harmony. First, you've got the structural system. That's the frame, the nose cone, the fins, basically everything holding it all together. Then, the big one, the propulsion system. The engine, the fuel, the oxidizer. You've got the payload system, which is what the rocket's actually carrying. And finally, the guidance system. That's the brains of the whole operation, with all its computers and sensors keeping the rocket right on course. Now, the propulsion system, that's the biggest part by far. But the payload is the entire reason we're doing this. And here's something that'll blow your mind. For a typical rocket, more than 90% of its total weight is just fuel and oxidizer. It's this famous problem called the tyranny of the rocket equation. It literally means you need a mountain of fuel just to lift a tiny payload off the ground. That precious cargo is really just the tiny tip of a very big iceberg. So we know what a rocket is made of, but now let's dig into the core physics that explains how it actually moves. And for that, we need to go way back, all the way to 1687 and a little guy named Sir Isaac Newton. This is it. This is the single most important principle in all of rocketry. For every action, there is an equal and opposite reaction. It's so elegant, so simple, and it's the fundamental reason anything, from a tiny balloon to a giant Saturn V, can fly. Think about this. You've definitely done this. You inflate a balloon, but you don't tie it. You just let it go. What happens? The air rushes out in one direction. That's the action. And in response, the balloon zips all over the place in the opposite direction. That's the reaction. A rocket does the exact same thing, just, on a much grander scale. It throws a huge mass of hot gas out of its nozzles at incredible speed. And that powerful action creates an equal and opposite reaction that pushes the rocket up, and away. Okay, so Newton's third law gives us the push. We get it. But how much of a push do we actually need? Well, that's where Newton's second law comes into play. This is the one that gives us the formula to figure out how much our rocket is actually going to move.
This law is really intuitive when you think about it. Imagine kicking a wiffle ball. It goes flying, right? Now use that exact same kick on a heavy bowling ball. The result is, well, it's totally different and your foot probably hurts. For the same amount of force, a more massive object is going to accelerate a whole lot less.
And this applies directly to launching stuff into space. The more things you want to send up, the heavier your satellite, the bigger your spacecraft, the more powerful your rocket engines have to be. It's that simple. You need to generate more force, or what we call thrust, to get that heavier mass moving and accelerate it all the way up to those insane speeds we need for orbit.
Okay, we've covered a lot of ground here, right? From the basic parts of a rocket to the laws of Sir Isaac Newton. So let's boil all of that down to the absolute key principles you need to remember about how this all works.
The first thing, and maybe the most staggering thing to really wrap your head around,
is the sheer speed involved. To stay in orbit, you have to be traveling at about 17,000 miles per hour. It's this extreme need for speed that pretty much dictates every single other thing about how a rocket is designed.
And here are the rest of the big takeaways. Remember, rockets work in space because they carry their own oxygen. They move because of Newton's third law, action-reaction. The amount of force they need is all about Newton's second law, force equals mass times acceleration. Every rocket is built from those four core systems. And finally, liftoff. Liftoff happens at that one precise moment when the upward force of the thrust is greater than the downward pull of gravity on the rocket's own weight.
You know, it's also really important to remember that this technology has a pretty complex and serious history. Modern rocketry was literally born from the V-2, which was a terrifying weapon developed in World War II. It was a huge technological leap that, after the war, was repurposed by scientists and engineers to become the very tool that kicked off the space age and, eventually, took humanity to the moon.
The science we've talked about today, the chemistry of combustion, the physics of Newton, that's what got us off this planet. It's incredibly powerful, but it definitely has its limits. So the real question for the next generation of explorers is, what's next? What new principles of science are going to power the rockets that take humanity not just to other planets, but maybe, one day, to other stars?